Nice to start the week out of school, right? So I'm going to talk to you a little bit about light today. You can do so many things with light. What are some of, and I said it's good to start the week with out of school, out of work, but I don't know about you. Monday mornings, I'm rather sleepy and groggy. So if I am going to be the only one standing here and talking, it's not going to work. So I really hope you interrupt me and ask questions. And I'm going to ask you questions, and I hope you will answer, okay? And no right or wrong. Answer what you think is correct. So my first question is, what do we use light for? What can you think of? So one of the first things, that's perfect answer, is illumination, right? The first thing we do is we switch on a light. And before we had lights, people used the sun for illumination. So that's, yes, one of the first things that we think of. Can you think of anything else? Well, at the end of this talk, I hope when I ask you that question, you'll have a lot to say. So I don't know if maybe we can switch off some of these lights. Yeah. We use it for illumination. It's also really beautiful. These are photos taken, that's in my campus in IIT Madras. That's somewhere on the beach. It's really beautiful. You can take beautiful pictures playing with light. But light has many, many, many uses, so many that I could spend a whole year and more telling you about them. And in this talk, I'm going to focus on a few things we can do with light and hope I give you an idea of all the possibilities. And one of the things that really commands our life these days, and how many of you own a phone? Okay. How many of you have used somebody's phone? Nearly everybody, right? Can you imagine your life, or even if you don't own a phone, can you imagine the life of your family without a phone? And when I say phone, I don't mean the gadget that you pick up and you call somebody and you talk and then you put it down, right? The phone today means so much more than that. Maybe you never use it to call and talk to somebody. Maybe you use it to message or watch a movie or something. That phone has a lot of light in it, light components, light devices, okay? And a lot of what we do today is connecting to the internet, right? And we use fiber optic cables. So that last picture down there, let me use the pointer. This is a bunch of fiber optic cables. You can't see the cables very clearly, but you can see the ends because the cables have light coming through them, and the ends are clear because you can see the light, okay? So communication using this. Okay. So what do we need to do to make light useful? We have the sun, we have the lights like you see over here. You have many different sources of light. This is a laser. I'm pointing with a laser. This is a laser pointer. So you have all kinds of light sources. You would have seen different kinds of light sources used for illumination. But if I want to be able to use light for something other than illumination, I must be able to control that light in some way. I can't use it for displaying a movie or sending communication, information, unless I manipulate the light. I control that light in some way. And so one of the first things I need to do in order to do that is to collect the light. Here I've taken an example of a solar collector. It's collecting solar light, and it could be used maybe to convert it to solar energy, right? Powered. But apart from just collecting the light, let's say I had the light from a laser. You can see you don't see the light traveling to the screen, but you can see it bouncing around on the screen. It's very bright and sharp. It's very different from sunlight. It's very focused and directed. But even this light needs to be controlled if I want to use it. So if I could use it and shape it, so the light that comes out of the laser, if I looked at it, it would look something like this. If I measured the power everywhere across the beam, it would look like this. But maybe I don't want a beam that looks like this. Maybe I want to cut a circle out. You know, cataract surgeries, you need to remove the lens that has got damaged. So you need to cut a ring out. And you can use a laser to do this. But you only need to give heat in a ring. You don't have to heat up the whole place. You need to heat up a ring and remove the lens. So maybe I want to convert a light beam that looks like this into a ring like this. Or maybe I have some industrial purpose and I need to convert this circular shape into a square shape. So I can design optical elements that will do this conversion, that will shape light for me. And shaping light again allows me or helps me to use the light. And of course, if I collect it and shape it, finally I'm going to use it. I put a very common application there, a camera, but of course there are many, many applications. And after this talk, you're going to be able to tell people when they say, what do you do with light? You'll say, oh, illumination is one of the things we do, but there's so many other things. Okay. So let's look at some of the applications. I've picked a handful. This one is a very powerful laser being used for cutting. Because light can be made to contain a lot of power, and because you can see it's so directed, it's so focused, I can use it to cut very neatly and very accurately without damaging the areas nearby. Lasers are used for cutting in surgery. Now, it's really important in surgery. Somebody is going to cut you open. You don't want them to use a jagged knife and say, oh, I'm not able to get through. Oh. Would you like that? No, I don't think so. Or maybe you can't feel it then, but you would sure feel it later. But a laser is very directed, very focused. You can cut neatly, smoothly, and not affect the nearby areas. So lasers are used in cutting in industrial. Here they're cutting metal, but they're used a lot in surgery. You can send lasers into the air, and you can see how it interacts with molecules in the air and dust in the air. So you can figure out about pollution, or maybe use it for studying clouds. So you can use it to study about the weather or about the atmosphere. You can use it in something called a smoke detector. So what's a smoke detector? Why do we use a smoke detector? So it makes a sound when a fire starts and you're alerted. How does it work? You have a laser and you have a detector, something that detects the light. And this beam of light is going to the detector all the time. If something blocks the path, and if the detector doesn't sense the light, it lets out a warning sound. And smoke will rise up and fill this area, and the amount of light reaching the detector is going to reduce, and therefore block the path. So it's such a simple idea, and yet it saves lives. Right? It's such a simple concept, and yet it saves lives. Many of you will be in buildings which have smoke detectors. So next time you look up and think, there's an optical device. That's a device which has a light source in it. Okay? Here is a magnified image of a butterfly wing. Right? Butterflies are beautiful even when they're not magnified. But if you zoom in on the wing of the butterfly, this is how the scales will look. You can use optics in a system called a microscope. And maybe some of you will have done labs or are going to do this in a lab where you will use an optical microscope and you can magnify. We normally can't see things that are smaller than a certain size, but you can magnify and look. Now this is beautiful, but it also tells us something about the structure, and that helps us understand nature. I could also take a blood sample and magnify it and look at the cells. And by looking at those cells, I could say, there's something wrong here, and maybe diagnose a disease. When a person has cancer, the cells will change shape and form. Now, if I take a sample of blood, how many of you have donated blood for something or had to have a blood test? Oh, good, not so many. That's good. But if they pull out that blood from a syringe and you see that syringe full of blood, you can't tell anything by looking at it. It goes for some testing, and a lot of that testing is maybe chemical testing, different kinds of testing. But one thing that they might do, depending on what they're looking for, is to look at that blood under a microscope. And by looking at the cells, by magnifying and looking, you can tell and diagnose about diseases. So it's optical microscopy is a very big field. This is a device called a pulse oximeter. If you visited anyone in hospital, or if you watch movies and someone's lying in a hospital bed, they'll have this thing clipped on their finger. And it is always telling the nurse or the nurses or doctors different things, but it's called pulse oximeter. It tells them how much oxygen there is in your blood. That's a level of how well your respiration system is working. Again, how does it work? It's clipped on your finger, and there's a laser and a detector, and it's sending light through your finger. Your hand is kind of, I don't know if you can see, you won't be able to see here, but your hand is translucent. Some light will get through. And by measuring the amounts of light through your finger, because blood with oxygen absorbs light differently from blood without oxygen or less oxygen, they can tell how much oxygen there is in your blood. They can also, this level also changes with your pulse, your heartbeat. So it will measure and tell the pulse of the person as well as the amount of oxygen in their blood, and both very important to monitor for someone who's ill or lying in an ICU. Okay. When you go shopping, you're at the checkout counter. Does the person look at each price and type out each price? What do they use? They use this, it's a barcode scanner. Maybe some of you use this Paytm to pay for things. It also scans something. How is it scanning? There's a light beam that is scanning over this code, this barcode here. This is an optical device. It's an optical device all of you would have seen. So I've just picked some very, very few examples to show you already when you walked in and you said illumination, you can already see that so many more things that you can do with light. Okay? Okay. Now I mentioned phones. How does a phone work? How do you call? How do I hold something here that's not connected physically to anything? And how am I able to call somebody somewhere else in the country or somewhere else in the city, somewhere else in the building? So if you take a phone, it sends out an electromagnetic radiation to a nearby tower, right? You would have all seen these towers all over the place. These towers work line of sight. So the information, the signal that goes to the tower gets sent to another tower that's visible to that tower. And it goes like this, tower to tower to tower, till it reaches the other person's phone. Now this is okay if you're making a call to someone fairly close by. But say you want to call somebody in another country. There may not be towers all along the way. Now earlier, the calls used to go through satellite. So you would do this tower to tower to tower and eventually to satellite. And from that satellite, again, send somewhere and then back tower to phone. But it takes a lot of time to do that, as we're going to see. So what is used these days for sending our conversations is they get converted from this sound energy, talking is sound energy, it gets converted to electrical energy, and from electrical energy into light. And that information, our voice, travels in the form of light through optical fibers from one place to another. This is a map of all the optical fibers all across the ocean bed. There are 880,000 kilometers of optical fiber that lie on the floor of the oceans. That's a huge number. Does anyone know what the diameter of the Earth is? Does anyone know the diameter of the Earth? Now you're wishing, if I had my phone, I could quickly check it up. Even a rough idea, is it 100 kilometers diameter? The central, no? Is it 100 kilometers? No, because the distance from here to Bangalore is 350 kilometers. Got to be more than that. Is it 1,000 kilometers? It's more than that, okay. Is it 10,000 kilometers? It's 12,700 and something kilometers, yes. Look at that number, 880,000 kilometers of fiber. That's roughly 70 times the diameter of the Earth is the amount of optical cable that's on the ocean floor. Did you know that? I was amazed when I learned this, that our oceans, I think my ocean is full of fish and sharks and nowadays, unfortunately, a lot of garbage. But I never thought that our ocean was full of optical fiber. But it is full of optical fiber, 880,000 kilometers crossing continents. So if you think before there was optical fiber, if you needed to make a phone call, you would pick up your phone, you would ring, and the person picks up and you say hello. And that hello would go to the satellite. And that satellite, the communication satellites are about 36,000 kilometers above. So let's say you're here and you're making a call. That signal has to travel 36,000 kilometers up to the satellite, and then from the satellite down to the person you're calling, so that's 2 times 36,000. And that person will reply, and that reply is going to go up from here and down from here, so that's 4 times 36,000. That's in kilometers, so I've made it into meters by multiplying by 1,000. And this is the speed of light, so it's traveling at 3 into 10 power 8 meters per second. And that means for you to exchange hellos, it took 0.48 seconds. Now let's do the same phone call and let's use optical fiber. You say hello, and it goes from here to here. I've chosen 2 points, okay, that are 2,700 kilometers apart. So the hello goes through that distance, the person replies, it comes back through that distance, so it's 2 times, I've taken this roughly as 2,800 kilometers. So it's just twice that into making this meters. It's traveling in fiber, so I don't know if you noticed the difference. Previously I'd said that velocity is 3 into 10 power 8 meters per second, but now the light is traveling in fiber, so it's a little bit slower. It's traveling at 2 into 10 power 8 meters per second, and that takes 0.028 seconds. It took 0.48 seconds there, and here it's 0.028 seconds. In a flash that this conversation is happening. So earlier when we made phone calls, you would actually hear the lag. You'll say hello, and then you wait. And then the person would say hello. And then you'll say something, and then you wait. And then you don't know if the person is going to speak, so sometimes you start speaking, and then they're speaking, and you get all confused. And now you hardly ever notice that lag when you're making a phone call, because it's traveling on the surface of the Earth in these fibers. And even though it's slower, even though it's going slower, it's still so much faster because the distance you're traveling is so much less. Okay. Now, how do I get light into a fiber? How do I do that? What is a fiber? A fiber is surprisingly, how do signals travel if you want to charge your phone or power up your refrigerator, or what is the source of power there? Are you using electricity? Right? And to make electrons flow, what kind of material do you need? What's a good material? You need conductors. Can you give me an example of a good conductor? Metals, copper is an excellent conductor, yes. Now, why can't I put metal cables? I mean, when I say optical fibers are under the ocean, of course they're protected and covered. They're not out like that. They've got a lot of protection. In fact, if you search the internet, you'll see pictures of sharks biting the cable. So you have to protect it from the salt water. You have to protect it from hungry sharks. So it's really protected well. Why can't I just put metal wires? Why do I use fiber? It turns out that wires are much more lossy. So by the time the signal travels these thousands of kilometers, it would have become too weak. So I need something that keeps the signal strength. And light in a fiber can travel much more distance than electricity in a wire. So a fiber is not made of a metal. It's not a good conductor. It's what you call a dielectric. A dielectric is not a good conductor. An example of a dielectric, can you give me an example of a dielectric? Okay. And something else, you're sitting on chairs. What are those chairs made of? Parts of it. You have wood. Wood is a conductor. What do we use as wood is a dielectric. What is the material we use as a dielectric for transporting light? It must not be, it's not a conductor, but it must be transparent to the light. Light has to be able to go through it. And what do we use? We use glass. So fibers, I've given you a small section of a fiber. It's a long, very thin piece of material that can stretch for thousands of kilometers. It is made of glass. And the glass is made very, very specially. It has an inner region and an outer region. So it's a very, very, very thin cylinder. But the cylinder has two parts, an inner and an outer region. And the inner region has something we call, it has a property, a refractive index, which is higher than the refractive index of the region around. Okay, I'm not sure. Have you heard the term refractive index before? Yes? Oh, good. What is refractive index? The danger of saying yes is you have to tell me what it is. Okay, we're going to come to what happens. You're telling me what happens when there's an index change and we're going to talk about that. But what's the definition of refractive index? So it's a ratio, very good, between the speed of light in air or vacuum divided by the speed of light in that particular medium or material. And here the medium is glass. Okay? So typical glasses have a refractive index of 1.5 because of course the speed of light in vacuum is the fastest. So anything else is going to be slower. But the refractive index here is a little bit higher than the refractive index here, and we'll see why that's important. Now what's the size? I said it's like a cylinder, but if you think of a cylinder, you think of this big block of thing and you can't bend it and fold it. And it's nothing like that. So what is the size of a cylinder, this cylinder? The inner core is 9 microns. A micron is 10 to the power minus 6 meters. Okay, what's a millimeter? 10 to the power minus 3 meters. A micron is 10 to the power minus 6. So a micron is 1,000 times smaller than a millimeter. And the inner core of a fiber is 9 microns, and the outer core of that fiber is 125 microns. Okay. Just to give you a sense of how very small that is. What's the thickness of your hair? Average hair of an Indian person. You can pull one out if you want, if you're feeling sleepy. What's the average thickness? No idea? You think it's in millimeters? So the average thickness of Indian person's hair is about 100 microns. So these fibers are just a little bit thicker than that. And these are what are carrying information, your phone calls, internet, the World Wide Web, is bouncing around in cylinders of glass that are a little less than the thickness of your hair. Okay? Now that sounds good. How do I get the light to stay inside this glass? Okay? I need that light to be trapped inside that glass. How are we going to do that? So let's look at why the fiber is made the way it is. If I send light, that's my light beam, making a certain angle, it's entering the fiber. I showed it like this because this fiber continues on and on and on and on, okay, thousands of kilometers. It's entering the fiber, and when it enters, now we get to the point that she said, what happens when light enters, or have you ever put a spoon inside a glass of water? It looks bent, you see that, right? Refraction, so it's going to refract. And because the refractive index here is larger, this light beam bends closer. So this dashed line we call the normal, and this light beam is going to come closer. This angle theta 2 is going to be smaller than this angle theta 1. Now it travels and it comes to a boundary here. What's the boundary? This has a different refractive index from this. So I'm going to have refraction again, right? Okay. Now this has a smaller refractive index. This angle is going to be larger. What happens next? If I could somehow make the light not refract out, but send all of it in, and then at this boundary, because it came, all of the light turned inward, over here, if all of the light turned inward, I could have all of the light bounce inside this core. And in that way, I could keep it trapped. So how do I do that? For that, we have to do something called Snell's law. Okay. Have you heard of Snell's law? No? Okay, so Snell's law is basically saying what happens to light at a boundary. Okay? I have light incident on a boundary. A boundary basically means I have one material of one refractive index and I have another material of another refractive index. We know light is going to refract at the interface. How does it refract? It doesn't do anything. It doesn't say, today I came in at this angle, let's say this is 30 degrees. It doesn't say today it's 30 degrees, so when I bend into this glass slab, I'm going to bend 50 degrees today, and tomorrow I'm going to bend 10 degrees. If you come in with the same angle and the materials have the same refractive index, every day it's going to bend in the same way. There's a rule that it follows, okay, and that rule is called Snell's law. And this is how it would bend. If we said NT is greater than NI, so if this is larger than this is how it's going to bend. Okay, that's the law. The refractive index multiplied by the sine of this angle is equal to this refractive index multiplied by the sine of this angle. That's the law, and that's how light will always travel through. Now the sine is a special function, okay? Have you learned about the sine function? Yes? What's the largest value the sine function can have? It can't become bigger than 1, right? So what happens here? If this is a constant, I'm not changing the medium here. If this is a constant, I'm not changing this medium. If I keep changing this angle, to keep this equation valid, this angle is also going to have to change, right? If I keep increasing this angle, theta t is also going to increase. It will always be less than theta I, but it's also going to increase, right? Let's look at that. For these angles, when theta is 0, sine theta is 0, and this is how sine theta changes all the way to 90 degrees, where it has its largest value of 1, okay? I'm going to take, in this example, that the glass slab has a refractive index of 1.5 and it's surrounded by air which has a refractive index of 1. So this is how the light bends. Change the angle of incidence, I change the angle of refraction, right? The transmitted angle is always less than the incident angle in this example. Now, let's change it around. Let's put the light in the medium of a larger refractive index. And remember, why am I doing this? Because the core of the fiber has a larger refractive index than the region around the fiber. So I'm sending in light into the middle of the fiber, and I want it to stay trapped. I don't want it to refract out. Okay? So let's say I do this. Let me just do the next one also. This beam bends so much. This beam bends this much. Now imagine I make the angle of incidence any larger. Let's say I make it a little larger. Won't this angle become 90 degrees? What happens if I make it even larger? Can the angle be larger than 90 degrees? It can be, in a sense. It means it's not refracting into this medium anymore, but it's coming back into this medium. So if I go on changing the angle, this is what happens. So if I have a large enough angle here, what happens is the light never leaves the glass slab, but is forced to reflect within the core of the fiber itself. We call this total internal reflection. Why? Because the light is forced to stay within the fiber itself. It can't leave. It only happens if the core of the fiber has a higher refractive index than the region around. And I ask you all to go do an experiment. It's a really simple experiment to do. Take a big bottle like a, I hate to say this, but like a Coke bottle, okay, the PET bottles, and make a little hole at the bottom and fill it with water. The water is going to come out of that hole like a cylinder of water. The water refractive index, does anyone know? You're really good, you're really sharp this morning. 1.33 and air is 1. Its refractive index is larger than the surrounding air. Now if you take a laser pointer and shine it through the water comes out like this from the bottle, from that hole at the bottom of the bottle. And what will the laser pointer do? The light is going to bounce around in that little spout of water. It's not going to leave. It's not going to come out straight like this. It will come in through the water. It's a simple experiment to do. Go back and do it. And you are doing a demonstration of how light travels in a fiber. You'll be doing a demonstration of how our fibers and our communication works. Okay? So maybe I skip a bit of this maths. The basic idea is above a certain angle, called the critical angle, in a medium of higher refractive index, light is always going to be forced to stay within the fiber. Okay? Okay. I am going to skip some of this maths now because I think you got the basic idea, and that is trapped light is what makes communication possible. Okay? And that's what makes it possible to send light thousands of kilometers across the ocean floor and give us access to information and people across the world. Okay. Beautiful pictures, right? These are pictures taken by somebody swimming underneath, like in a pond or in the sea, looking upward. And can you see in all these pictures, there's a dark circle around. They've not done anything special to get that dark circle. Most of the time we don't think about what fish are seeing, but this is how a fish sees. Every time a fish looks up, if a fish looks up, this is what it's seeing. It sees the lit up area and a dark circle. And now that you understand total internal reflection, you should be able to think about why is there a dark circle? The water has a higher refractive index than the air outside. And this is why there's always a dark circle. Because this light goes, if the light is coming in this path, but the nice thing about light is, if I find out this is the path light traces in this direction, I can assume this is exactly what happens in the opposite direction. Now, because of total internal reflection, or because of this being a higher refractive index, the light that is incident at 90 degrees, this beam is almost 90 degrees, it gets bent, and this whole view of the outside world gets squashed into this cone. And this region appears dark, and this region appears dark, and everything that's visible here is actually squashed into the smaller cone, and that is why this is the view that you would get. And because it's based on refraction, this is actually called Snell's window, okay? And this is what a fish would see, but if you ever have the opportunity to go swimming a little deep underwater, have a look up and see if you can see Snell's window. Okay. Now, I don't have much time, but we will try to squeeze in one more application, okay? That's my finger. I took a photo of it with my cell phone. Now, it's not that I have this really nice finger and I want to share it with you. I wanted to show you my fingerprint. Can you see my fingerprint? Nah, so I haven't done a very good job. Why do you think fingerprints are important? Identify for Aadhaar. Now, if that's going to be the first answer, Aadhaar, yeah. Okay. How many of you like watching murder mysteries and police shows? Oh, suddenly a lot of activity. Okay. Don't fingerprints get used there all the time? In the show, they get a fingerprint of something, and 15 minutes later, they have identified the criminal. Well, in real life, it doesn't happen that fast, but yes, that's the idea. You can use it for identification because each one of us has a unique fingerprint. Now, if that's how I'm going to capture my fingerprint, it's not going to work at all. How would I ever identify anybody or anything? I need pictures that look like this. Now, why is it difficult to capture the fingerprint? Why is it so difficult? To answer that, let's look at this picture. Oh, I already told you what it is. This is India Gate. Where is it? And why does it look like that? What happens in Delhi all the time? Pollution, that horrible thing that we do to our planet. So yeah, forget that it makes for bad pictures, it's killing us also, but it's making for a bad picture. I cannot see India Gate very well because of the pollution. On a clear day, this is how it would look. These pictures are taken actually around the same time. What made this picture clear? What made this picture clear and this look like this? It is the pollution, but what did that do to the art of taking the picture? It meant the contrast over here is so much clearer. That's why it's clear, because the contrast between the structure I want to photograph and the sky behind is very high. There's a big difference, whereas the difference here is very low. And that's why this makes the India Gate look so blurry and unclear, whereas it's so clear over here. So if I want to take a picture of my fingerprint or anyone's fingerprint, I somehow have to increase that contrast. I have to make it look different. And how can I do that? So we use a fingerprint sensor, and if any of you have given your Aadhaar registration, you would have had to register your fingers. You would have used such a sensor. How does it work? It uses light. It has a big glass prism. Now, this is supposed to be a finger. I thought it was very clear. My daughter looked at it and said, you better tell them it's a finger, otherwise they are not going to know. So, this is a finger, okay? This horrible stuff over here is not dirt. It is a fingerprint amplifier. I made it make it look bigger. So of course it doesn't look that big. But what is a fingerprint? It's ridges and grooves, right? So I've magnified that so you can see it clearly. You press your finger. Do you remember how you did it for Aadhaar? You had to press on this surface. So you press your finger on this glass prism. You might not have known that, but there was a glass prism underneath. And you send light in. Now, the regions here have air actually in them because there's a little ridge. So between the ridges, you have air. And you have your finger in the other places. So what happens to the light? This has a larger refractive index than these regions here. If you get the angle of illumination correct, now you should be able to tell me if the light is in a region of higher refractive index, what can happen when it hits that boundary? Total internal reflection. Is that what you were saying? Right? So it will come to this part of your finger, and that part of the light only is going to totally internally reflect. But what happens to the part of this light that hits this surface and this region and this region? There the refractive index is not, this is not higher than this. So what's going to happen to that light? That light is just going to go through. So now I've created a contrast. In regions where there are air gaps, light comes back. In regions where the finger is actually touching, light goes through the finger. And so I have regions where it's bright and regions where it's dark, and I get this nice clear image. So I can't just take a photograph using a regular camera, but I can enhance the contrast, and I can do this. Okay? Okay, I'm not going to go into the third application because I can see it's almost close to 10:30. But I hope that these two applications give you an idea. The next application was actually about CDs, but let me skip ahead right to the end. Okay, so in this talk, I talked to you about communication, fiber optics. I talked to you about a fingerprint sensor. We didn't get to a CD player, but a CD player is also an optical device. So I've given you an overview of just some of the few things you can do with light. Okay? And you notice that most of the things we've done with light have been very multidisciplinary. They're not just physics related. They use optics, they use physics, they use engineering. We use lasers, we use different colors of lasers, wavelengths are colors. We use a property called interference. I didn't cover that, it was in the CD part. And of course, there's electronics, there's software, there's maths, there's computer science. And in the CD player, we would have even used some physiology. Physiology is study of the human body. We would have even used knowledge of that to compress data and to store it. So it's very multidisciplinary. You don't have to stick to one area of science, but light is there everywhere. So now I hope when you look at a device, you will pick up your phone and say, hey, this is an optical device. You will look at that smoke detector and say, hey, this is an optical device. And I hope you'll be busy catching the optics in the world around you, and I hope that inspires you, if not to a career, at least to have a great deal of fun with the world. Thank you.
Thanks, Shanti. So we have time for a few questions, if some of you would like to ask something more now, before the break.
Monday morning.
Maybe it's also easier to ask questions during the break. So you will be here for another half an hour.
I'll be here for another half an hour.
So during the break also you can talk to her. And last chance, any questions that you would like to ask here, now? No. Okay, okay. So thank you once again, Shanti. Let's all thank her.